So a sensor, this is going to be on just about every start. It's about to convert a physical stimulus into an electrical equivalent. And then we're going to look at something called transfer function. It's the ratio between the physical stimulus and the electrical equivalent. So physical stimulus in, electrical equivalent out. You count close. I mean, it's a ratio, which means we divide, right? So we're going to start off with position. We'll look at the potentiometers, optical rotary encoders, linear optical encoders, linear variable differential transformers, or LVDT. We'll look at photoelectric. We'll cover those in the next section because these can be used as positions, and they can also be used as different types of things. Ultrasonic and vision. In fact, vision will be the last thing we cover. We don't have any labs on this. So, potentiometers, first of all, we have two types of pots. The human ear does not hear in a straight line. So, we have on your radio and stuff, if it uses a potentiometer, most of it now is totally digital. But if you ever got into a real low radio, if you looked at the volume control, it's just a potentiometer. So what we're trying to do is be able to, if you set the potentiometer halfway, you want your volume to be half sound, right? To understand, but that's not the way our ears hear. So audio tapered pot, this guide is not a linear pot, so its ohms does not vary at a constant rate. So we wouldn't use these for sensors. So what we're going to do is use a linear tapered pot. So that means if I got a linear tapered pot, and it's a 10K pot, that means if I set the wiper in the middle, it would be a 5K. So that's what we're dealing with. We'll look at slider wipers. We'll talk about the transfer function, setting the span, also in the loading area. We're gonna make sure we understand this because if you take the AEC 208 and you want to take the Siemens Level 1 certification, they actually have a question on there about setting the span and loading area and linearity. So this is basically a single turn pot. We call it a single turn pot, even though it's impossible to get a single turn out of it. These things are going to be around 350, 320 degrees that you can rotate them. What they do is they basically have a resistor. It's just a film that's on the pot. I've got one somewhere. I wish I'll look for it. And then what you do is you slide a contact across that resistor, which gives us the ability to get a different resistance reading between 3 and 2 and 1 and 2. So technically the leads are numbered 1 through 3. The center lead, or what we call the wiper, is always going to be in the middle on these turn pots. Well, I'm not going to say always. Normally it's in the middle, because odds are that you might run into that. And as we move the potentiometer, the control, whatever's moving this. By the way, if it's a 10K pot, then between 1 and 3, you're going to measure 10K. That's what we mean. It's 10K pot. That's what it measures between 1 and 3. What varies is what we measure between 2 and 3 or 2 and 1, depending on which one you use as a common. Then what we do is we come over here. So basically a pot ends up with something like this. And then this would be the wiper. So this is a variable voltage divider. So if I come up here and if I put 20 volts right here and I reference this as common, then that means if I put the pot all the way up here at the top, it would give me 20 volts. If I put the pot all the way at the bottom, it would give me a 0 volts. And then I could get any, if I was accurate enough and the pot had a good resolution, I could literally get an infinite number of voltages between 0 and 20. impossible for us to set it at exactly 12 volts. So these are variable voltage dividers. By the way, we can take the pot and we can take the wiper and connect it to one side, and this acts like a rheostat. Or how you spell rheostat? I like that. So you'll see this done a lot. So when they figure this out, it's basically done away with rheostat. It's that every time we buy a rheostat. So with a pot, I can make it serve two functions. I can make it serve as the rheostat, or I can make it serve as a voltage divider, a variable voltage divider. And what we're doing is we're constantly changing the ratio of these two resistors depending on where we set it at. So what moves the wiper? Now what moves the wiper? A knob, or we can connect it to something, right? I understand. If I connect it to something, then the voltage that I get out would be the position. The voltage we get out would represent the position. So you're right, on ours we move a knob. So there on the trainers, if you use the variable voltage divider, you're setting the voltage with a knob. That's actually a real thing. So these are multi-turn. We have single-turn pots. We call it a single-turn, but it don't do a single-turn. We have multi-turn pots that allow you. So we have like a 10-turn pot. We have what we call 5-turn pots where you can actually get more than one turn out of it. So you get more than 360 degrees or 320 degrees. I think our pots that we have that we're going to do our lab on, I think they max out about 320 degrees. And then we have linear pots, which basically work exactly the same way. But these move, this will allow us to move in a linear position. And then what we do is we use the wiper, we use the pin 2, we use that voltage to represent a position. So like this one, so this is a good example. So here's a pot connected to a motor shaft. And so as the motor turns, it would give us a position. So this is what you're doing. When you turn that wiper, this gives you the value of R A to B. So they're calling B the wiper. And so what we can do is we can change the ratio between that. And so what we're doing is we're changing the ratio of our voltage. And of course, it's going to have a tolerance, so it's still not perfect. But it's probably going to be, if I need something that's perfect, then odds are we're not going to use a pot. If I need to know the exact position. Because it's got that tolerance in there, right? Are we okay? Yes or no?
Why would you want to use a pot since you already? What would be the usage?
So we can sense the position of a motor. We can sense the position of a shaft. The exact position, we're not sensing if it's at a spot. We're just sensing what range it's in. And it's very simple to use. I mean, there are other methods. So I doubt out at Rosa if you have any pots, you might. We've got one on the Festo line, and what they do is they have and we've got one on the Amtro line. So what they do is we have a cylinder, and then they raise it up, and then they have a potentiometer. They have a flat thing, and this goes over to a potentiometer. And what happens is when it comes up and hits that thing, it moves the pot, and the pot gives us a voltage that represents the height. And then we're using that. Over on the end, the very end, they have a linear pot in that thing. So as the carriage moves across, pin 2 gives us a voltage that represents the position. So it's very simple to do, and then we can bring that into some device where that resistance or that voltage represents the exact position. So we have 2 of them over there on the two. So it wouldn't surprise me if they don't have one somewhere. It's very simple. We can process it with a programmable controller really, really easy. And it's cheap. These things are really cheap. A lot cheaper than encoders. That's a really good question. So we got 2 manufacturing lines over there, and both of them use these guys, both of them use a potentiometer to check position, but it's actually giving us height, right? You understand? One of them is truly a position. So what it does is it moves across. We have magazines down at the bottom, and we can program it to stop. It knows when it's a magazine when it gets a certain voltage. Unfortunately, it's not in the program now. They're using optical interrupters over there, but we can add it because they able to. So what I like about the Amatro line is it's got more stuff than it needs. So a lot of the stuff that's available is not in the programs that's currently running in the PLC. That's a good question. Very simple, really, really simple. On some of the other position sensors that we have, this is probably one of the simplest ones. All you got to do is figure out how to attach it to whatever you want to sense the position. So we're not saying we're going to deal with rotary pods, but they're easy for us to do, and we're going to turn the knob with our hands, and then we're going to figure out what voltage we should get if we set up a certain degree. So we'll figure what we call a transfer function. So yeah, these things. So I said they might not be out there, but it wouldn't surprise me. So these sensors are very, very cheap. So good question. Any more? So before this voltage means something, we have to come with something called a transfer function. And transfer functions are usually set on out, what you get out, and what you put in. So on this one, we're going to get volts out, and of course, we're going to use this to measure degrees, right? We're going to use this to measure position. So what we do is we take the maximum degree, so this would be a 350 degree pot, linear pot, and the maximum we would get out at 350 degrees is 10 volts. So I'm getting what out? I'm getting volts out, 10 volts, and that's the maximum I can get out, and that's going to represent 350 degrees. So anybody got their calculator? The transfer function is going to be in volts per, it's going to be volts per degree.
0.028.
Don't say 0.02. We could round it, but we'll figure out how to round it. So 28 millivolts per degree. 28 point what? 5 millivolts per degree. Per degree. So what should I expect to get out of this? Well, they've already got one. What should I expect to get out at 30 degrees?
At 30 degrees?
At 30 degrees. I'll take my transfer function, that's volts per degree, and then I'll multiply it by the number of degrees. So I'd say 28.5 milli times 30 degrees, and that would give me the voltage I should expect. Times the volts per degree. So that stands for volts for every degree I get. For every degree, let's say, instead of say per, for every degree I get 28.5 millivolts. So that's what we call volts per degree. So now if I know the transfer function, I could give you any degree, and you should be able to tell me what voltage I'm going to get out. That makes sense? So 75, 150, 175 degrees, which is right in the center. Multiply that by 28.5 millivolts, and it should come up and give you 5 volts, depending on how much you round. So what do we got? What did we get at 30 degrees? 857 millivolts. And what would we get at 200 degrees? Huh? 5.7. I knew it had to be above this because I know what half is, right? So that could be right. So what we do, once we got the transfer function on this sensor, then I know what to expect to get out of the sensor. And we're going to get volts, but then I could translate that into degrees, which would be easy to do with a PLC. By the way, PLC 2 will learn math. So I could take the voltage and multiply it times what? That times the transfer function and display degrees on the PLC. Very, very easy. That's one advantage we get out of a programmable controller. It's a computer. So not only can it do relay logic, it can also do things that a computer could do. So it does math. So we could very easily take this voltage. We could very easily take this voltage, this transfer function, and convert it over to degrees. All right, okay? Any questions? So transfer function is usually what? It's what we get out divided by what we put in, out over in. And then once we get that transfer function, this really comes into play with a lot of our analog sensors. Because our analog sensors are going to give us a voltage or a current that represents something. And then it's up to me as a technician to know what that is, right? You understand? To know what that current means and to know what that voltage means. So yeah, the PLCs we have now have analog digital converters in them, so we'd have to figure out another transfer. All right, okay. So this is one of the first labs we're going to do is we're going to go over there on the trainer. We're going to give y'all a potentiometer. It's got a compass. I got a compass that you can put the pot on, and we'll put some tape over there so you can tape it down. You'll come up and measure the number of degrees first. Like I said, ours don't quite give us 250 degrees. I think ours is around 320. I can't remember the voltage we're going to put across it. Of course, the voltage level is pretty important, right? You understand? Because if you calculate it for 10 volts and you got 11 volts up there, then your pressure function comes to be out a little bit. So this would be a nice regulated power supply. That's true on just about all these devices. And the size of the pot, the ohms of the pot really doesn't make any difference, right? You understand? It's just that the smaller the pot is, the more precise it can be. So if I had a 10K pot, then that's going to be volts per 10K. It's going to be harder to adjust than a 1K pot. And a 1K pot would consume more power just sitting there by itself. So 10 over 350 equals 228.6 millivolts per degree. Then at 82 degrees, we should expect 2.35 volts, or close to it. Depends on how much you round, right? Everybody okay there? Any questions? You have to do that on test. Linear potentiometer. So we have a maximum voltage. It's the max voltage over the pot length or the degree. So it would be on a linear pot. It's going to be the maximum length of the pot. So it's going to be like 10 inches or 5 inches or something like that. And then the pot over there on the manufacturing line, that sucker must be probably 36 inches. I have to go measure it. So what you would do on that one is you would have so many what? Inches per foot, yeah. So we have a 10-inch pot and, we have 12 volt supply, maximum is 12 volts, right? 12-inch linear pot with 10 volt supply, it moves 8 inches. What will be the output? I wish I didn't pop up the answers, so I would like y'all to actually do that. So what do? We take the maximum voltage out, divide it by the length. Since this is inches, it's going to be millivolts per inch, or this many millivolts for every inch. You don't want to say per. So this, we use this symbol a lot, and it's a symbol. So in math, we use it to indicate division, but when we're talking about lengths or ratios, it's per. You have to say per inch. So people don't understand that these are symbols, and a symbol is when you use one thing to represent something else, right? So it can mean different things since it's a symbol. So 10 divided by 12 is 833.33 millivolts per inch. So I take that and multiply it by the number of inches. And I would get 9.6 volts. Are we okay there? Yes, no? We have to take in consideration gear ratios. So this guy is, by the way, on gears you can tell what's going to happen. So this right here would be what we call a speed multiplier. So it wouldn't create much torque, but it would be a speed multiplier. This would definitely have to be a multi-turn pot. So it's got a 3-to-1 gear ratio. So that means the output is going to be turning twice as fast, or 3 times as fast as the input, or it's going to go 3 times the distance. So over here, this guy right here is moving 90 degrees, but my potentiometer actually moves 270 degrees. Y'all understand that? Yes or no? Huh? So what would we do? How would we do the transfer function over here? This is the guy right here we want to measure. We don't want to measure that. We want to measure the distance of our motor. So how would we do that?
How many turns there?
So what would we do? So let's say 370 degrees is the maximum and we get 12 volts. But what would we do to calculate a transfer function?
You have to go 12 divided by 300, whatever you said. The max volt divided by the max degree.
Yeah, but that would give us our transfer function up here. What we want is we don't want 270 degrees. We want it to tell us 90 degrees.
So would that be the max volt? That would be the max degree there, right?
Right. But what we want is this would be, yeah, you're right. So this would be the maximum degree here, right?
Do you use your voltage with that degree?
Yes. That makes sense? So you have to figure out the gear ratio if you go through gears. So here my transfer function would be my voltage. What did I say?
12.
Yeah, 12 volts divided by 9. Because that's what we're trying to sense. So when we get this voltage out, then that would say, okay, it's at 90 degrees. No, it's like a 6. So what would our transfer function be?
33 millivolts per degree. I mean,
It keeps repeating. So what should we get at 45 degrees? Should get 6. Let's just make sure it works out. Did it work out good too?
Mhm.
Okay.
That 45?
That 45, which would be half of 90.
Right.
So if we got this at 90 degrees, then we should get half of that at 45 degrees, right? But we just check to make sure that our transfer function is right.
What's the total?
Should be 45 degrees.
Not that.
And I'm sorry, it should be 6 volts. So my output should be equal to 45 times that, 133.3 millivolts. And hopefully it comes up to be 6 volts. If it does, we mean we got our transfer function right. It's always good to put something that you know what the answer should be, and then check out to see if the transfer function comes up and gives you the right answer. So here we're using the potentiometer to give us a voltage, but the voltage is not the degree, it's the voltage that represents that degree. This would be hard to do with a regular control system, but with a PLC, they don't have any problem. Well, it's programmed right. PLC says for programmable logic control. So the person that's bringing this voltage in, if the PLC's got an analog into it, and we've got two, the compact logic that we got several analog inputs on it. The 1100 that we have in PLC 1's got 2 analog inputs on it. The Siemens 1214 has 2 analog inputs, and then we have what they call a signal module that we put out that gives us an analog output. Here we're not going to talk about analog outputs because what we're doing is sensing position. So I bring this into my control system, and my control system would have to translate 6 volts into 45 degrees. Now you could calibrate a meter with a resistor to do that. Setting the span determines the voltage desired at the top and the bottom of the potentiometer. Determines it is about. So what we can do with a pot is we can determine what minimum voltage and what maximum voltage we get out of it. So right now we're either getting 0 or we're getting 20. But let's say we wanted 0 to be 2 volts. So that way we can measure plus and minus positions, right? Does that make sense? So we have the ability to do what we call set the span. Calculate the size of the resistor needed to drop the remaining voltage. So what we could do is we could do it like this. So this is an example of a fuel gauge. So this is basically the way your fuel gauge works. So that's another example. So anybody ever took the fuel sensor out of the gas tank? And you'll see it's got a little float on it. And it just moves the pod. That's a perfect example. But we set the span. Here, the problem is my computer is looking for 0 to 10 volts, which is standard on a PLC. So PLCs, most PLCs that I've seen on a voltage analog input, that's the span right there, 0 to 10 volts. But our car is on a 12 volt system. Actually, it's not really 12 volts, so we can use that just to make sure we understand it. So what we're going to do is we want the output to be 10 volts when it's full and 0 volts when it's empty. But we're going to apply this with a 12 volt system. So notice the first thing we did was added a pod in there. We added into the top of our pod, we added a what? A resistor. So I mean, as soon as I see that resistor, there's no way I can have 12 volts with it. So what we would do is we would, did they teach y'all the voltage divider formula in DC? So we can calculate this. If I call this just for math purposes, I call this R1 and R2. Then I can calculate the voltage drop across, and when we calculate the voltage divider, we treat it like a fixed resistor. So this is what we're looking at. That's what we're looking at right there. So we're looking at a 1K, and we're looking at a 5K. And we're calling this R1 and R2. And then I put 12 volts right there, and what we're trying to do is figure out what's at the top of that resistor right there, because that's going to set our maximum voltage that we can get out. So voltage divider formula, if we use this, we don't have to calculate the current. So VR2 would be equal to the ratio, which would be equal 5K divided by 6K. So it's R, so the formula is VRX equals to RX over RT times VS. So I know right off the bat that it's going to drop. So the K's are going to cancel. You'll understand? They're on the top and the bottom. So right off the bat, I know I'm going to have 5/6 of the voltage down there. And then I multiply this times 12. What do we end up at the top of the pot? 5 divided by 6 plus 12. Huh? 10. So we end up with 10 volts right there. So when I calculated my transfer function, I would not use 12 because 12 is not across the pot. I would use it for what? I would use 10. So what we've done is we've set the span. So I'm powering this up on 12 volts, but I want my span to be 10 to 0. So we're using resistors to set the span.
Why did you not use 1K and you don't use 5K?
Because that's the way that it's set up. I could use, this right there could be a 10K and a 50K. That right there could be a 100K and a 500K. Any two resistors that give us the same ratio would still give us 10 volts. So I did not use this. Siemens used this. This is off the Siemens test code.
Well, I'm referring to, you said RX indicates in the formula that I could use R1 or R2, right? Either one.
No, it's
Okay.
RX, the one I want to, well, this is the one, you're right, I could use either one, but this is the one we want. This sets the span. That guy right there, this guy is looking for the span. That guy right there is just to set the span. So I want to know, here's my common. So I want to know the voltage drop across R2. I don't care about the voltage drop across R1. Okay. So it's whatever resistor you want to find the voltage drop. So yeah, I could come up here. If I used a 1K, it would say, okay, it's going to drop 2 volts. Well, what in the world does that have to do with what this guy sees? Understand what we're saying, Mario? Okay. So the resistor you want the voltage drop across. So which one do we want the voltage drop across? We want it across R2, right? You understand? Divided by what? RT. So I want it across the 5K. So it's the resistor you want the voltage drop across, 5K divided by RT. And a lot of times you can do that in your head. 6K, the K cancels out. So I know right off the bat that this resistor right here is going to drop 4/5 of the voltage, no matter what voltage you put on it. Now, what's nice about this formula, most of the time in DC, you'll say, okay, I got a 5K and a 10K, and I put 12 volts across the circuit. What would the voltage drop be? Okay, and you would say, okay, that would be 12K divided by 6K. That's going to give me I. Then I take I and multiply it by my resistors, and that would give me the voltage drop. But then I'd say, okay, let's put 15 volts across it. And what would most of y'all do? You'd recalculate current again. And this guy right there has no different. It has absolutely no reference to the voltage that's applied to it. So this resistor right here would drop 5/6 of the voltage, whether you put 20 volts across it, 5 volts across it, 8 volts across it. This resistor is always going to, the ratio of the resistor is always going to not change, right? You understand that? So I guarantee you in DC, if I would have done that, I said, okay, let's raise this up to 15 volts. Most of y'all would have said 6K, 15 volts divided by 6K, then you took that current and multiplied it and got that voltage drop. when all you would have had to do in your calculator is just take that ratio up there and multiply it by whatever voltage you apply to the circuit. So this is what's nice about the voltage divider formula for series circuits, is that you don't have to recalculate current every time. So in solid state, we use this a lot. Because we're not concerned with the current, we're just concerned with the voltage that's biasing our solid state value. So it's what? It's the resistor you want the voltage drop across, divided by the total resistance of the circuit. That gives you the ratio that resistor would drop no matter what voltage you apply to the circuit, and then you multiply it by the voltage applied to the circuit, and that'll tell you the voltage. So if I had 15 series resistors, and I wanted to find the voltage drop across R3, then I could just say R3 divided by RT and multiply it times the voltage. Now I say, let's raise the voltage up or let's lower the voltage down. That resistor would always drop this ratio in a series circuit. And I've happened that before too. I say, okay, calculate your current, and then what happens if I change to a 6K? And one of the answers in DC would say the current would be the same because it's a series circuit, but it's not the same circuit. You'd be surprised how many people answer that. So what would happen if we put a resistor down at the bottom? Let's say I come over here, because this is my pot. Make this this. Okay. And let's say this is 1K, this is 5K, and let's make this a 1K. What would be the span of my pot? This is pretty easy because they're both 1Ks. We know these two resistors right here is going to drop the same voltage. So they're the same size in a series circuit, and since the current is the same and the resistance is the same, and did I give you all applied voltage? So what would be the span of my pot? So what would be the maximum voltage I would get out of my potentiometer, and what would be the minimum voltage I would get out of it? So my maximum voltage is not going to be 12, and my minimum voltage is not going to be 0. So the voltage drop across this resistor affects what this guy is going to be. The voltage drop across this resistor would set what this is supposed to be. You understand what I said? Of course, we're going to have to use some Kirchhoff's law. Probably the easiest if you did this one, you did this.
So you do the potentiometer with 5K, about 12?
No, it's R, it's the voltage drop across the resistor divided by RT. So if I wanted the voltage drop across the 5K, it would be, if we call this R1, we call this R2 before, we call this R3. Then the voltage across R2 would be equal to 5K divided by 7K. We change our ratio. And what's nice about K, you can do that off the bat. You can do what? You can just drop the K because it's on top and bottom. So the 5K, then I'd multiply this times 12. So what would my 5K drop? 8.57. Now the 1K, so VR1 would drop 1K over 7K. First K's cancel times 12. What's that? 1.7. Okay. So this guy right here, and so this guy here is going to drop what? This guy right here is gonna drop what? 1.71. Alright. So what would that leave me right here? 8.57. This guy over here is gonna drop 1.71. So what would be my span?
What would be your what?
What would be my span? What voltages would I get to transfer my transfer function? What voltages would I get over off out of my
You
part?
calculate those, you add those together?
Well, I've got plus 5.8.57 on the top. I got plus 1.7 on the bottom. My span would be, my maximum I would get out of my pot would be 8.57 volts. My minimum I would get out of my pot would be 1.71. I understand that. So what we've done is we're not on, now we're not using 0 as our bottom number. So the bottom would be set by this resistor, the top would be set by this one. So all you have to do is take this one, find the voltage drop across this one, or R3, find the voltage drop across that, and you don't really need to find the voltage drop across that one. So the maximum I would get out of my pot is 8.57 volts. My minimum I would get out of my pot is 1.71. So using a pot, we can set the span. So our span don't have to be all this voltage and this voltage. We can actually set the span. So the lower voltage is not equal to 0, and the top voltage is not equal. Does that make sense? So we'll have to do this in lab. The lab that we're going to do is I'm going to give you this, and then you'll have to actually see what I'm talking about. It's always better, to do it hands-on than it is to do it on the board. This is the first lab. The first lab we're going to do is going to be with a potentiometer. Okay, guys, I'll go ahead and take another 10-minute break. I didn't. Most modern computers or controllers are digital devices. A lot of the quantities that need to be measured are analog. So where do y'all run into an analog and digital converter here at the school? You have one. You had to buy one. Part of your test equipment. So it's a multimeter. So your multimeter is measuring analog devices, but it's displaying digital information, right? You understand that? So what that means is inside your meter, there has to be a device called an analog to digital converter. And it uses what they call an integrator, which is very, 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 very accurate, but it's really slow. A lot of quantities that need to be measured are analog, so analog to digital will convert. An analog to digital convert will convert an analog quantity to a digital. We have different methods. We'll look at the one that's primarily used by a programmable controller. Like I said, your meter is extremely accurate, so it uses what they call an integrator, which is really, really neat. And it's set on a number of counts. So one of the things when you buy a meter is you're looking at the number of counts that's available. So the higher the count, the more accurate the meter will be. So if it's got a and you can tell by the way the meter ranges. So if your meter ranges on 199 or something like that, then it's a 2,000 count meter. If it ranges on 399, then it's a 4,000 count meter. If it ranges on 599, then it's a 6,000 count meter, and it would have a lot higher resolution, but it would cost a lot of money. Our PLCs use just a standard A to D converter. It uses the way the circuit is made up is pretty complex for the PLC. So we have single bit A to D converters. This is primarily the most often used. This is real easy to bring into a programmable controller. We bring it into a binary input and we just see if it's on or off. But so this would not actually enter measures a quantity for us, what this would do, it would tell us when that input exceeded a certain value. If it's below a certain value or above a certain value. So all the sensors, except for the pressure sensor, I think the pressure sensor has an analog output on it, but they didn't bring it out for us. And we looked at this, right? Well, some of the digital sensors have a adjustment, so you can actually adjust where it trips. Over on the Festo line, we have 3 colored cylinders that we deal with. We have a chrome plated, and we have a red, and then we have a black. And the sensor that it's using is dependent on reflective light. There's no such thing as solid black, so even black reflects some light off of it. So what we can do with the sensors is we can adjust it so it don't see black. We can adjust them so sometimes they see black and sometimes they don't see black. And it uses that to determine how it puts the cylinder together. So these have a span adjust on it, right? Where you can set where it trips at. But an analog to digital converter. So this is basically what a program logic controller has in it. It has an A to D converter that gives us a binary count that indicates what the analog value that we're measuring. And the more bits we use, the better the resolution. So what we do is this one has 1, 2, 3, 4, 5, 6, 7, 8 bits. And you have to know this to program the PLC, by the way. What you would do is you would come up and figure out how many numerical combinations you would have by the A to D converter. So we can calculate the number of numerical combinations by taking the base. So like if I said, how many counts can I get out of base 10 using 2 digits? Well, that would give us what? That would give us 100, which means I could count from 0 to 99. Well, on binary is a base 2 numbering system. So if I've got 8 bits, that means 2 to the 8, that would give me 256 combinations. So that would give me 0 through 255. The Micrologic 1100s have a 10-bit A to D converter. So it would be 2 to the 10th, which would be 1024. The Siemens have a 12-bit A to D converter, so that would be 8,192 combinations if you split it. So the more bits you have, the more memory it's going to take up inside the PLC, but the better the resolution. So the 8 bits is okay. So that means that. So what we would do is, this is a little different, is we take the voltage, the maximum voltage that we get out, and we divide it by the number of steps or combinations we can get out of it. So if I apply 10 volts, I've got A to D converter that gives me 8 bits. That's going to be 39.11 millivolts per count. So you can see, so this thing is going to miss some voltage. So let's say I have millivolts per counts per millivolt, per volt, yeah. So what that means was if I have a space of 390.11 millivolts between when it actually counts. So the more bits you have, the better resolution you have. That makes sense? Probably not. So what we would have to do is we have to figure out what our maximum output is, which was in our situation is 10 volts. So if I take 10 volts and I divide it by the maximum number of steps, that's 39 millivolts per step, right? So if I put 6 volts into it, then I do the math, and that's going to give me 151, a count of 151. got right here in binary. Anybody know how to go from binary to decimal? Now luckily, our program controller does the conversion for you. So if I was looking at my A to D converter, and I brought this information in, it would show 151. Okay? And you can make it display binary, but if we wanted to convert binary, what you do is you start with 1, then you double it every time. 2, 4, 8, 16, 32, 64, 128. So what we would do is we'd add every one of them that's got a 1, so I'd add 256, 1, 2, 4, 8, 6, and then I would add 16. No, I must have missed one because that's not the right number. That's going to be embarrassing. Make sure I didn't miss one. I'll have to go back and redo my slide. So this would be 1, 2, 4, 8, 16, 32, 64, 128. That makes me feel better. Somehow I got one count off. And then you just add the 1s. So I'd be, you don't have to know this first class, by the way. I'd this, and then I'd add 16, sorry. And then I'd add 7, and that should come up and give me 151. What's nice about a computer is that it can display things that are not really there. So if you come up here and look at this real close, you see that all these are made up of just a bunch of little dots, little squares. So all the computer knows is when it sees the code for a T, it's got in its memory the pattern to display a T on the screen. So everything you see up here is done with 1s and 0s. So what's nice, even on your computer, is even though all your computer understands is this, it sees this, but it displays it as that on your screen. So the PLC does exactly the same thing. So on a programmable controller, the main base that is going to display everything, unless you tell it to do different, is going to be in decimal. So I mean, if I brought this in into my PLC program, it's going to display 151. But what we're going to have to do now is we're going to have to figure out a transfer function to determine what 151 means. Does that make sense? Yes or no? So how would I do that? So let's say 151 represents 60 degrees. So what would be my transfer function inside my PLC? So this is what we would do. 60 degrees, it's not volts, it's just degrees.
Okay, we know degrees now.
Yeah.
So degrees would be it's the maximum divided by the maximum. So the maximum degree divided by the maximum.
Well, no, all we know is that 151 equals to 60 degrees. By maximum, it's going to be 255.
You divide 60 degrees by 1.
Yeah. So if I've got a standard, I don't have to use the maximum divided by the input, right? If I know that 151 equals 60 degrees, then I can do that. So the maximum count we would get would be 255. And then 255 would give, the maximum I would get would be 255, and then the maximum degrees might be 320. So right now I'm saying, okay, 151 equals to 60 degrees. Well, all we have to do with our program is just multiply 151 by that transfer function, and it would give us the degrees. So what do you say? We take what, 60 divided by 151?
Yeah, 397, and then we.
It's not a volt. It's a transfer function has no, a transfer function would be degrees per count is what our transfer function would be. But it technically don't have a unit like volts or stuff like that. This is milli, right?
It'll be milli what?
It would be, so this is degrees, so it would be degrees per count. So when you're doing ratios, your top number comes first and your bottom number comes next. So that means I could take, when it comes, I could, inside my program, I could bring my count in, and then I could multiply it using a math function and multiply it by, 397 milli, and then it would display 60. So that's what you have to do in your program. You have to figure out, okay, what does this count equal? What does this count equal? Does it equal temperature? Does it equal watt? Right? So it might equal 30 degrees in temperature, if you're measuring a temperature sensor. And then you can take the temperature that you know, like we know, like freezing, and then you can divide that by what you actually get out of it, and you can calculate it this way. So that would be, we'd have to use the math instruction, the multiply instruction. So what's nice about a programmable logic controller is that it does math. So if you can calculate these transfer functions, you can take these analog sensors and display the quantity that you want. And not the 151. The 151 doesn't really mean anything when it actually means 60 degrees, or it might be 60 degrees of motion, it might be a 60 degree temperature. So analog to digital converters, we're going to run into a lot of these, and on a PLC, when a programmable logic controller, you'll have to figure out the transfer function, because you're going to have to do the math to make the PLC display the actual quantity, not the binary number that it represents. And the more you have, the more bits you have, the more accurate it is. So like I said, the MicroLogic 1100 we have has a 10-bit A/D converter. So that'd be 2 raised to the 10, which is 1024, and then we subtract 1, so that means we could split that thing up into 1023 different steps. And then a 12-bit A/D converter, which is on our 12.14, would be 4096. So we could take that sucker and divide it, we take that and divide it by 4096, so it would have a lot better resolution. So the more bits that your A/D converter has inside your programmable logic controller, the more accurate you're going to be, but it's still not going to be perfect, because you still have a voltage between each count, right, to understand. But the narrower you can make that voltage between each count, the better it is. And this is also true on digital to analog converters. If anybody's had AC and they use our digital scopes out there, when you look at that sine wave, if you look real close, you can actually see it moves in little steps. Because it's an analog, it's going through a digital to analog converter, and it's going from an analog to digital converter, and it's not perfect because we have a space between the steps, right? You understand that? So even when you go from digital to analog, your analog signal is not going to be perfect. It's going to be a little steps depending on the size of the number of bits that your digital analog converter has. So look at that on that oscilloscope. If I had that analog scope that's back there in the back, that the Tektronix, the sine wave, the waveform would be perfect, because it's showing you what's there. A digital oscilloscope has to go from analog to digital, and it's displaying digital information. So, but they're nice because you can store with them. So this would be the math. Of course, this is not the math you'll have to do. You can always come back. We're not going to do this on a test, but what I'm just trying to show you is what you would have to go through, like if you had a programmable controller, when it gives you 5 volts, when your analog sensor gives you 5 volts, you're going to have to make 5 volts mean something, right? You understand that? So this is where the transfer functions would really, really come into play. If you're programming a programmable controller. And this is the math. So in our field, we can't get by without math. You say, we know we're ever gonna use this. Well, by George, if you get into the field and you're programming a PLC and it's got analog inputs, you're gonna have to know what this does, right? So y'all can always come back and reference this. I think y'all still have access to it. Y'all still have access to the old blackboard?
I don't think I,
No, we still do. Of course, it's gonna give you a warning because they're not paying for the, secured site anymore. So they might have took it offline. So we're still pulling stuff off of it. So I used to have a printer over here. I don't know if I still got it. I need to stick it in the storage room somewhere. So another thing we use to check positions is rotary code. PLCs love this thing. And the math is a lot simpler. A lot of times you still have to figure out a transfer function. We have two. We have absolute encoders and we have incremental encoders. And then we have two subcategories. They can either be rotary or they could be linear. I went backwards, guys. So this is an absolute encoder. So these guys are either going to put out binary or they're going to put out a code they call a gray code. And these usually use different types of sensors. One we got uses a Holotech that we'll talk a little bit about. So this would be this would have 4 tracks. So absolute encoders have to have a track for every count, and it doubles every time. So that means if I wanted to add one more bit, I would have to add another wheel. If I added another bit, I had to have another wheel, another band in my code. This has only got four bands. So that means it's got one, and it uses something to sense where it's at. So normally these things, especially if they're in a really good environment, they'll have a photo sensor that we're talking about. Well, they'll have a transmitter on this side, and then they'll have a receiver. And then we would have one of these for each band. And what it does is it passes light through. So right here, if the light gets through, on all through, down this line right here, then it would give me this count right here. And then this right here would be a 1. You can do that 1, 2, 4, 8 across the top. So this right here would be a 1, this would be a 2, this would be a 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the maximum count would be what we talked about before. I'd take the number of bits, 2 to the 4th, which would be 16, and then we do away with 0. So we subtract 1, so the maximum number I would have would be 16. Now what's nice about an absolute encoder is that if I stop my system and turn power off, and I come back the next day and turn power on, the absolute encoder is still going to show me where this device is at. But the problem is it gets very cumbersome because if I wanted 2 to the 5th, which would be 32, I'd have to add another bank, right? If I wanted 64, I'd have to add another bank. If I wanted 128, I'd have to add another bank. And so the more resolution, the more accurate they are. So look at the spacing between these. So as long as this thing was in this range right here, it would say it was at position 1. A. But what's nice about it is that it holds its position even when we don't have power on. So these are called absolute encoders. Robots said they use this kind of line, but it appears to be an absolute encoder. So they call it a battery backed up absolute encoder. So this is but if we only have this and the robot's got, good gracious, let's tell them how many counts. So whatever we want to measure the position of, we just position this. And then as it goes across, it gives us a count indicating the location. then we would have to interpret the count to be a certain position. So this is only a 3-band. So 3-band would be 2 to the 3rd, which is 8, minus 1 would give us a count from 0 to 7. So this came off of YouTube, off the Learning Channel. GE, what country is GE? That's all it's about. Denmark and Russia. So absolute encoder. What advantage does an absolute encoder have? Well, the absolute encoder, it keeps its position. We don't have to keep up with it. It keeps
So the light is going to
the open slot, yeah.
Okay.
Yeah, you can actually see it up there. It's pretty neat. And then it's got an optical sensor, which we call through the beam. We'll look at that. So this is one of the optical sensors that we'll talk about.
On the previous slide, at the side of it had black areas caused 1 output. What does that mean? Just do you count it?
Yeah, so the black area is called the 1. So over here, and since there's no black areas, then this would give me back this right here. Okay, the black area is called the 1. So this would give me a 0, 0, 0, 1. This would give me a 0, 0, 1, 0. This give me a 0, 0, 1, 1. Make sense now?
Yeah. Okay.
Any more questions? It all depends on how you sense it and how you calibrate it and what it does. We're going to have 1 band. If I go, and it increases in powers of 2. So that means right now we have 16 counts from 0 to 16. If I add 1 more band, if I can add 1 more band, then that would give me 2 to the 5th, which is 32. So we can count from 0 to 32. If I add 1 more band, that's going to be 10 to the 6th, which would be 64. And then it runs. So the more bands we add, so 0 and 1, that would give me 2 counts. The closer I come in, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. Keep it up with 8,192, 16,000. So I've dealt with binary a lot, guys. So this would be an absolute encoder. And it's got so you can't hardly see the bands. It looks like it's got 1, 2, 3, 4, 5, 6, 7, 8, 9. And look what happens. It looks like it's got 10 bands. But every time the bands get over, everything gets closer together. So 2 bands, that'd be 2 to the 10th, which is 1024. So even with all these bands, we could only represent positions between 0 and 1023. And you can see as I add bands, the little gaps get smaller and smaller and smaller and smaller, which it's going to be a lot harder to sense. 1024 is pretty good, but in the world of robotics, this right here just wasn't fun. The resolution that we have on robots, we're down in the nanometers on how accurate those things are, and these guys right here, even though they call them absolute encoders, they're cheap. They're cheap because it's a unit. It's a unit that you buy. So this would be a linear absolute encoder. This actually came off a printer. I wish I could find I got an HP printer, dot metric printers in here, and you can actually see the linear encoder. And the lines, the spacing is so close. The lines are actually looks like gray. They're actually not. This is not an absolute encoder. This would be what we're looking at next. Of course, this I did this for you. So this would be counting in binary from 0 to 31, which would give us 32 counts. So this would be five bands. Wrong way, Rich. So this would be a binary encoder. So we need to know the difference between this. We don't actually need to know it, but we need to know when they start talking about these encoders, if it's a binary or a gray code. The problem we have with binary is we have a term in digital we call propagation delay. This is how long it takes these counts to propagate through a circuit. And the problem we have is that the more bits you have, the longer it takes to propagate through the circuit. The more bits that change. So when I count from a 0 to a 1, how many bits change? 1. Okay, when I count from a 1 to a 2, how many bits change? 2. And when I count from a 2 to a 3, how many bits change? 1. When I count from a 3 to a 4, how many bits change? 3. So you can see the problem we have with binary is the delay in the count would vary between counts. So what would happen is that these binary counters have problems with extremely high speed devices. You know, so if I've got a motor running at 7,200 RPM and I want to use this as a position sensor, then there's no way in the world that that binary counter can keep up with that. So what they did is they came up with a code called the gray code. And now code is when we use something to represent something. A code is when one thing's used to represent another thing. Codes, well, we have the ASCII code, Unicode, BCD, gray code, Unicode. Y'all, I mean, you use this all the time. So when I send information up here on the screen, it's binary, so it's going to be a code. So I don't know if you've ever noticed, but when you come over here and you say, I want to insert, and then I want to insert a symbol. Oh, okay, let's see. It won't let me insert a symbol. It still won't let me insert a symbol. So this is Word. I don't know why it wouldn't let me do it on PowerPoint, but these are symbols. So right now it's got the symbol for the number pi. That's the code right there. So the code that it's storing in memory, that it uses to display the pattern, would actually be don't disappear. It would be 0, 0, let's see, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. So that's the actual pattern, the code that it uses. This is a different base to represent pi. So this is what gets stored in your memory. It don't know what that is, but it knows that when it sees this code, it knows the bit pattern to display on the screen, to display pi. And so there's the letter, this goes all the way up to just standard characters. So there's the letter A. So that's the code that it stores in memory, in the video memory. Your video memory has all these dot patterns built into it, in the ROM. When it sees this code, it turns on the pattern for an A on the screen. So whatever we're doing is everything inside the computer has to be represented by a code, right? You understand? Everything we do. So this is a really good example. I wish I could have done it over there. Y'all probably seen this 100 times, but you didn't notice that the actual code that it's being used. So that would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. In digital, you're going to learn how to convert this over. Some of y'all probably already know. This is actually a number system called hexadecimal, which is what we use to represent large binary numbers. So that's that would be 16 digits, which gives us 65,536 combinations of characters. And you can go all the way down through here. Sometimes when you go to a place, it tells you that it don't have the character. So right now, whatever these codes are, this is not represented. So when they send you an emojicon, it sends you a code, and that emojicon has to be inside your phone, right? You understand, for it to pop up. And you can look up the Unicodes for emojicons. Emojicons. There you go. Unicodes. So here's the Unicode over here. You can't really see it. So this picture is stored in the memory of your computer, the dot pattern. They send you this Unicode right here. It looks that up in a bit pattern, and this is what it displays on the screen. So now y'all know how emojicons work. And of course, if you don't have it, what does it display? It displays something weird up there if you don't have it. So, yeah. So this is moved into 5 hex digits, which would be a big one. That would be 5.4. That'd be a 20-bit number. So we still haven't run out of codes for emojicons. So everything your computer does is represented by binary. So we use a bunch of codes. So we use binary to represent numbers, but we also use binary to represent codes. And that's something that happens all the time. Everybody comes out with a new emojicon nowadays. You have to download the codes before you get access to them. Where's my PowerPoint? So what they did is they came up with a code called the Gray code. It's a counting code. It is not a numbering system. It's a code. So this has to be translated. So this is Gray code, and it's a high-speed counting code. It's a code. It's not weighted. We can't use that 1, 2, 4, 8 number system, copy this out. There's a method of converting it, but we really don't need to know that. All we need to know is a high-speed code. So this is the decimal number that it represents. And when I go from a 0 to a 1, how many bits change? 1. When I go from a 0 to 2, how many bits change? 1. When I go from a 2 to a 3, how many bits change? 1. Yeah. So no matter which way we go, whether we count up or count down, between every count there's only 1 bit change. So basically this does almost the propagation delay would be the same no matter what. So the Gray code is a high-speed counting code. So some of your encoders you'll run into, these absolute encoders, they're going to be Gray code encoders, right? You understand that? And some of them might be binary encoders. That make sense? So this is the way you convert it, by the way. I'm not going to do it. So this is a Gray code encoder. So notice it don't go 1, 2. So 2, if I did that in binary, we'd actually say it was a 3, but it's a Gray code encoder. So all these are not going to be the same, but you need to have basic difference of a Gray code. So Gray code is a what? It's a high-speed counting code where only 1 digit changes between counts. So this is Gray code encoding. I don't know where I got that animation at. I need to find out if I can get credit for it. I didn't do it. Even though we did have an application at one time where we could make these animated GIFs. So this would be a Gray code. This would be an absolute encoder. Whether it's Gray code or not, I can't tell because the tracks are so small. And that would be the sensor. Incremental encoders. These guys are very, very simple. all these do is they give us a sequence of pulses and we count pulses. The only problem we have with this, so an absolute encoder, we would know the direction. So if it turned one way, the counts would go positive, and if it turned the other one, they would start going from high to low. So that's another advantage of an absolute encoder is that we know direction. Incremental encoders don't know direction. They work real well unless we do something. Well, I'll show you what we do. If they work real well to give us position that's moving in one direction. So these guys give us a series of pulses. And then we count them. And every count would mean something. So these are what we use these in combination with a counter. And then we count. PLC has counters in them. And by the way, if you use one of these, you'll have to figure out what they call a high-speed counter, which would have, if those things are designed to handle these encoders like this. So this is also a Unipackard printer. This guy here was used to sense the page, the length of the page. So it knew how far to advance the paper for every line. But it gets a bunch of dashes. Now, what usually happens on your printer when you turn it on? Well, what it's doing is establishing the zero. So what it does, it'll do that seek over to the left-hand side, and then it finds itself. So what we have to do with incremental encoders is we have to start them from a known position. Robots, we call it mastering. So you have to master the robot. So if you ever lose the contents of your encoders, then none of your programs will run because it don't know what. They don't know what, where it starts from. So this is one disadvantage of an incremental encoder, is that one thing, you have to start it from a known position. So we set zero somewhere. So if you ever look at a robot, it's got marks on it. And we call it it's not a perfect mastering, it's called I forgot what they call it. It's close enough, but if you want it to be exactly right, then you have to get a calibration jig and mount it on there. And touch it up against something. But most of the time what we do, we can get it within a millimeter or so. Move the robot to the marks that's on the robot, and then we tell it that that's zero. We call that it's called some type of mastering calibration, I can't remember. So this is the old mouse. If you ever took an old mouse apart, and these are the encoders. You can actually see the encoder wheel in them. And then these are the sensors. These guys can sense direction, so we have to show you how they do that. So here we got a bunch of these track all around. The problem we have with these is that they get goop built up all the time, just rolling across the table. There's stuff in here that starts slipping. And the balls, you'd have to take them out every once in a while. And the track balls, you'd have to take them out every once in a while and clean them. And then clean off the actual things that spun the encoder. These are the switches for your left and opposite. Now we have a photoelectric mice that basically looks at the grain of the surface that you're on, which is pretty good. So you don't clean all those very much. So this is what we do to determine direction on an incremental encoder, is that we have two sensors, and they're actually offset by 90 degrees. So can y'all see where they got the two sensors up there? Here. So we have channel A and channel B. That's what they call them now, A and B. And so on this one, if it's turning in one direction, then on this one, which one occurs first? Yeah, B is occurring first. Now, on this one, which one is occurring first? So here A is occurring first. So what we can do on these quadrature incremental encoders is we get two signals out. We can count one per position, or we can count two per position. So if you had some way you can count the rising edge on both of them, you get twice the resolution. And we do have these, guys, by the way, guys, so we can actually see these on the oscilloscope. And what happens is when you change direction, then one leads the other. So with a quadrature encoder, not only can we use these to sense position, but we can also use to sense what? Direction. It's pretty neat. So these are quadrature encoders. And we do have some of these here. We don't have enough for everybody to do a lab on. In fact, we have to teach our oscilloscope if you haven't had AC. So you can actually see this. Now this right here doesn't actually mean anything until we do what? Until we run this through a counter. So what we have to do is we have to count it. So the resolution of incremental encoders are set by how far can your counter count. So that's the way the robot goes. It's got counters on the encoder. So if you ever took and actually look at the encoder, it's an electronic circuit card, and it's got counters on there. And of course, robots you can move up or move down, so those are got to be quadrature encoders, so it knows which direction to go. So it's got the counters in there as part of the encoder. So they call them absolute encoders, but they're not really absolute encoders. It's just that they appear to be absolute encoders by the controller. So what's the advantage of quadrature encoders? Not only can we use them to sense direction or position, we can use them to sense which direction they're going. So that would tell our counters to count up or count down, right, from 0. The problem we have with robots is that if you lose power to your counters, the robot doesn't know where it's at anymore. So what you'll find out about robots is they have batteries that we have to replace in. And what those batteries do is they keep the count on those encoders. So if you ever let those batteries run down and you turn off the power to the robot, then you're going to lose your count. And then you'll have to remaster the robot. So it's usually part of the preventive maintenance schedule where they go out to all these robots and they swap those batteries out. If they do that at Bros, they go out and change the batteries out every once in a while.
That happened the other day
If you leave power on, and usually we have no problem because they leave power on 24 hours a day, 7 days a week. And as long as the robot's powered up, you're okay. It's just that something happens. So if they go over there to work on the thing and they kill the power on it, then they lose their count. You can recalibrate it, by the way, without the batteries in there, but next time you lose power, you're going to use it. So that would be a good thing they could do on a preventive maintenance, is just to go out every one. Well, that depends. The Fanuc robots uses regular alkaline batteries, so it's very, very cheap on those to go out and change the batteries on the robot because it's no big deal. You know, a couple of the big Fanucs have 4D batteries, and the small Fanucs use 4C size batteries, just regular alkaline batteries. But the batteries on the ABB, you have to buy that from them. Those are like $240 a piece. So I can understand. So on our robots, we don't change those batteries out until the robot doesn't work, and then we just remaster it and let them use it until we buy the batteries. And most companies can't afford to master the robot. It takes a little while, to master it, and it depends on how accurate you want it. So yeah, I'm glad. So they lost their 0 on their back on one of their robots. So they call them absolute encoders because they look like they are, but if they was absolute encoders, we wouldn't have to keep batteries on them. So yeah, so all these robots have an access panel. You can get to the batteries. The ABB, we had to take off the back of it. It was so this is an animation of a incremental encoder. So the counters inside of, the regular counters inside of PLC are done by program. What's nice about a program is you can vary it, but what happens is that the program counters inside of PLC cannot keep up with these incremental encoders. So all your PLCs now have what they call high-speed counters, which they've gone back to hardware. So they have hardware counters in there that keep up, primarily to keep up with these things. If you ever seen a robot move, some of them are very, very impressive. So we really don't need to know this. We need to know the difference between a regular and incremental encoder. So an incremental encoder will give us a position, but it will not give us direction. And a quadrature incremental encoder will not only give us position, but it also gives us direction. So now we know the position of something, whether it's left, right, or right, left, or up or down, don't understand that. So odds are, as far as the encoder goes, the ones that fit position, odds are they're going to be a quadrature encoder. But you got to understand, these incremental encoders, we can use these for two different things. Not only can we use them to sense position, but the rate of the pulses could also tell us the what? Starts with an S. Speed. So this is a big advantage we have of an incremental encoder. It serves two functions. So on a robot, not only, especially if you're doing a control path move, you not only you specify a position, but you specify a speed. So it's no big deal because they can get the speed off the incremental encoders too, right? Because of the rate of the pulses. So incremental encoders are really, really popular out there. But if we lose power, we lose our count. So this is why when you start up your printer or you turn your printer on, it has to find itself, right? Or if you have a paper jam and you pull that paper out, then it's got to do what? It's got to find itself. So that's the biggest problem with this. We have to start from a zero. These increment encoders, if I'm using position, I have to start with zero. If I'm using them to set speed, it don't make any difference. Because all we're doing is counting the rate of pulses. Elevator usually, what, to sense position? They probably use photoelectric sensors or something like that because they don't need to know if you're between the first and second floor. They just need to know when you arrive at the second floor. So even on the counts. Like I said, printers use these, conveyor belts use these, robots use these. These are where we want to know where it's at between point A and point B. Not only do we want to know when it gets to the second floor, we want to know where it's at between the second floor. Unfortunately, elevators don't tell us that. So they wouldn't use one of these. They might use it to sense speed of how fast the elevator's moving. But that's a good question. Okay, so probably not on an elevator. Now they use something similar to this on your anti-lock brake system on your car, where it senses this wheel over here is still in motion and this wheel over here is not, and instead of just hitting the brakes, it pulses them. They use something similar to this, but they use a magnetic field instead of light.
What about the emergency brake? Does it look like something like that?
No, because here we want to know position. So on an anti-lock brake system, what they're trying to do is, of course, we learned a long time. Used to, we have to do it ourselves. Is that we do it now, but used to when you slammed on your brakes, what would happen? All four wheels would lock up and you wouldn't stop. Right? So what they learned was if you pat the wheels like this off and on, it has a tendency not to slide. Well, what they need to know is they need to know what's going on with the wheels. So you slam on the brakes, and this one stops, and this one's still spinning, right? Or your car's still in motion. So they use sensors similar to this. They use magnetics instead of optics to sense what wheels are in motion. But this would be on all your wheels of your car now. So it senses if the car is, you're telling the car to stop and the car is not stopping, right? So what does it automatically do? You can actually feel it sometimes. You know, you've been going 80 miles an hour on the interstate, and you get off of an off ramp, you don't slow down, and you hit the brakes, and you can actually feel your car, you can actually feel the analog brakes on it. That's helped a lot of stuff. Our cars are getting so dang smart. So quadrature encoders give us, they're incremental encoders, but they have these offset sensors that give us, not only can we use them to sense position, but we can also sense the direction. This talks about the encoders on a robot. So they call them absolute encoders, but it's a misnomer of the name because they're absolute encoders. They're not absolute encoders but they appear to be an absolute encoder because the counters are part of the encoder. How we doing? Nobody raised their hand. So let's see how many more slides we got here. I know these long lecture slides give us a hard time there. But we don't have very many. So as soon as we finish this, we'll go ahead and cut out. What determines when we induce a voltage magnetically? What do we need to induce a voltage magnetically? Let's start off. We need number one. We gotta have a magnetic field, right? Number two, we gotta have a conductor. Number three, we gotta have what we refer to as relative motion, which means one's got to move across the other. What determines the amount and strength of the field. Number two would be the number of conductor loops. I left out the end. Huh?
It's a number.
Yeah, I knew that. I knew that would get a laugh out of you. Three would be the speed of the motion. And we use metal to concentrate the field. So what's happening is the core of the transformer is moving. This winding is generated in one direction, this winding in one direction. This secondary winding is wound in the other direction. So they oppose each other. So when this one is putting out a plus, this one over here would be putting out a minus. And of course, so what's happened is they're pushing against each other, right? And what would happen, it would cancel each other out. So what we do when it's in the center, then we get 0 volts. And then if it starts moving in this direction, this guy gets more metal, it increases the strength of the magnetic field, which means this output would go up, right? Oh, this is the net. I think, yeah, this is the net. So in the center, 0. When it moves this direction, this would be this, and when they subtract each other, that's what we would get out. When it moves the other direction, this one would go up, this one right here would go up, this one would go up, this right here would go down, and this would be the net. So what we can tell with this thing is, if it gets bigger and it's in this phase, then that means it's moving in that direction. And the bigger it is, it means the further it's moving in this direction. When it moves in this direction, this guy's going to occur first. So you can see they're out of phase with each other. So when this is negative, this one's positive. And so what we can do is we can tell by which occurs first, which phase occurs first, we can tell the direction, and then we can use the amplitude to determine the position. That makes sense? So if it moves this way, one of them gets bigger, one of them gets less. If it moves this way, and if it's right in the center, we get zero. And so here, this is going to take some pretty sophisticated electronics to figure out where this thing's at. We know when it's in the, because you got to figure out which phase is occurring first, and then of course with the amplitude. So this is called a linear differential transform. You'll probably run into some of these in fluid power systems, especially hydraulic systems. In fact, somebody, I think they worked for Gaston, that said they had some of these LVDTs on some of their cylinders out there. This is just another demonstration of the same thing. This is a cutaway view of one. They look like a shock absorber. That's what they look like. A shock absorber. They're small. And they fill them up. They're very, very rugged. So this animation is really good. So this is the primary. This would be the output.
Oh, this moving, I see that moving up there.
Yeah. So they're actually showing it's moved. Well, notice it moves toward the green. It moves toward the blue. And then they're actually showing you the actual This is a really good animation right here. It comes from this guy right here.
What is the design? Okay, I see it. So, I was gonna actually got that top, let's see what it's.
Yeah, it's actually showing you the phase shift up there. It's an animation on the upper right hand side. So this is what they look like. So they look kind of like what? They kind of look like shock absorbers. And then, of course, it takes quite a bit of electronics to figure these things out. This is available to you, so it would tell you, so LVTs have to run in conjunction with electronics that figures out where it's at. And then we have a resolver. So these guys are linear. A resolver works exactly the same way, guys, but it's for rotary sensors. We had these guys when I worked on the airplane. These guys actually sense the position of the flaps and the ailerons and everything, where everything was. That's just that. So that's it for position sensors. Is this all of them? No, but it's quite a few of them. So I know y'all ready to get out. But any questions? Okay, I'll once I get the Make sure if you come in late like that, Scott, you make sure I get you on roll, okay? You did? If you sent it this morning, I don't. They said they brought us some. They said they're in a paper sack. I said they put them in the office. Yeah, I find it. So this ain't as big as the other one, but yeah, we got this too. Right there. It's very deep. Maybe still big.
That's the robot down there or something, right?
Oh, you get that out? A little further. Program to get it.
I'm just moving it around, because I can't get it to pull up. That's what I was doing before I had it up here. Well, no, I couldn't find, it's pushing it towards the, it's on the website. Or the program for, but I couldn't find it. I was at their website. When I found the, where it says, I can't find the download or play with or.
Okay, what are we gonna do? Well, you're doing the project class, right?
Yes, sir. Well, I can go up there. You don't know what class right now? Oh. Did you wipe this one? Oh, okay.
We work them all the way down.
Oh, I didn't know that.
That's for everybody. Yeah, just put it on that table up there. Look up there by the shelf. Thank you, thank you. What's that?
The stuff you're going over now probably is like a refresher. Trust me, you're gonna need.
Yeah, I'll remember.
Because, like, I kept mixing up the licenses, like, triggering versus.
Third thing.
Yeah, still on that.
A TIE fighter. See, I think about like the symbol for a crystal, not a TIE fighter. I can understand. Are you watching The Mandalorian? Yeah, but they only do 8 episodes.
But it's a one-time thing, right? As long as you start at the end of it,
The two the two they picked up at the very last, they're supposed to start their own series too.
Yeah, both had
Yeah,
and,
both sides.
I gotta go to the because, that whole incident. Yeah. The stop trooper, I can't remember her name.
Oh yeah, she's a marshal. I can't remember. She's tough.
But they fired her for conservative tweets.
Oh yeah, I read that, but I couldn't figure out who it was. But I remember.
And then,
Really? Of course, he wears a face mask all the time, so except every once in a while. So they could probably replace him with just about anybody.
I think John Favreau might be putting. Well, he's the whole reason Star Wars got revived. What's her name that's running it? Done a terrible job. No one wants